Hello and welcome to another Arlington High School Math 4 Honors video. My name is Kirk Weiler, and today we're going to be doing Unit 4, Lesson Number 4, A Different Look at Tangent Slopes. In the last lesson, we were able to investigate, using our graphing calculator, the property of smooth functions called local linearity, where we would zoom in more and more, and eventually what would happen is that any smooth curve would eventually start to behave like a line. All right, a line with a constant slope. We were able to approximate the exact slope of the tangent line by picking off 2 points on either side of where we wanted the tangent line and finding the average rate of change. Today, we're going to look at a little bit of a different way of getting at that tangent slope. Ultimately, the slope's still the same, but we're going to use a slightly different process which is going to lead us to a way of figuring out the exact tangent slope. But let's jump right into it. Alright, so we're going to return to our simplest nonlinear function, f of x equals x squared. We have already conjectured that its exact tangent slope at x equals 2 is 4. Now let's look at it a different way. So again, just to keep in mind what I'm talking about here. The idea is if we took y equals x squared, yeah, I know I got the graph right here, I see it, but I'll explain what I'm doing here. And I went to the point 2, 4, and then I drew in, oh, good, it's already there. I drew in this exact tangent line. What I would find is that its slope is 4. All right? Now, what we're going to do is we're going to experiment with that again, except we're going to do it in a slightly different way. All right? What we're going to do is we're going to draw a secant line. All right? A secant line is one that cuts across the curve at least 2 points. All right? And what we're going to do is we're going to fix that point at 2, 4, and then we're going to have another point at a and a squared. All right? And we're going to come up with the slope of that line for various values of a. And what we're going to do is we're going to allow a to get closer and closer to 2. All right? But we're always going to fix our x1, y1 point, if you will, to be the point 2, 4. All right? The only thing that's going to change will be our x2, y2 point. Now we're still going to use our calculator quite a bit. And in fact, let's jump into it right now. Let's bring up that TI-84 Plus. All right, there it is. And now what we're going to do is we're going to be finding the average rate of change, again, the delta y divided by delta x for various intervals. All right. Again, we're going to always fix the point 2, 4. And this will be then the x-coordinate of our second point. And as you see, what's happening is I'm going to let that x-coordinate get closer and closer to 2, but never get there because then, of course, we would have 0 divided by 0 in terms of the slope form. So let's start with our calculator right away and figure out the average rate of change, if you will, over the interval 2, 3. Now, because 3 is such a nice number, it's easy enough on our calculator to figure out that, of course, what we have is we have the point 2, 4, and we have the point 3, 9, right? So let's do that calculation. Let's just do it on our calculator. I know we could probably do it without the calculator. I'm sure we could do it without the calculator, but this is the way it would look. All right, parentheses, 9 minus 4, parentheses, divided by 3 minus 2, parentheses. Enter. All right, now, obviously, we're going to get there a slope of 5. So I'm just going to fill that right in. Now we could continue to do this, but of course the x2, y2, especially the y2, is going to get a lot uglier once these decimals get introduced. So I'm going to figure out a way on my calculator to really make it much easier. You know, remember, average rate of change, whoops, is f of b minus f of a divided by b minus a, the slope formula, okay? But I can really systematize that with my calculator. Watch what I'm going to do when my second x value is 2.5. Remember, I'm keeping my first point at 2, 4. So watch what I do on my calculator. Let me clear out the screen right now so that we're not looking at what we just put in. Now watch, I'm going to put in parentheses, 2.5 squared, right? That's f of b. well, I'm going to even though I know y1 is 4, I'm going to put it in as 2 squared. So minus 2 squared, parentheses, divided by, parentheses, 2.5 minus 2, parentheses. All right, make sure that calculation's all correct with all the parentheses there. Let you catch up a little bit. Let me catch up a little bit. And now let's hit enter. All right, great. And we get a slope of 4.5. See, what I like about doing it that way is it really hammers home the idea of, look, I've got two x values, a and b, 2 and 2.5, what have you, and I'm routing them into the function, right? Doing what the function says to do to them, which is square them, all right? And then I'm dividing by their difference. So let's do one more at 2.1 and then have you fill out the rest of that table. Then we'll go on to b as well. All right? So, parentheses, 2.1 squared minus 2 squared, parentheses, divided by, parentheses, 2.1 minus 2, parentheses. Enter. And that gives me a slope of 4.1. All right. So, what I'd like you to do is, using this technique or any other technique, calculate the average rate of change for the rest of the x2 values in the first table, in table from letter A. Okay, pause the video now and finish that out. All right. So what you should have gotten was 4.01, 4.001, and 4.0001. Please don't take like the pattern with the zeros up here and the zeros down here too much to heart. The pattern is real. It is definitely happening, but it's happening because of the peculiarities of the function y equals x squared. Not all functions in general would have a pattern like that. All right. Now, one thing I think I can say for certain is that as this second x2 coordinate heads towards 2, it definitely looks like the slope, delta y divided by delta x, is headed towards 4. But of course, x2 is headed towards 2 from the right? Maybe it would change if x2 was headed towards 2 from the left. Now, my students are going to jump all over me because I've been telling them all along, man, I always want delta x to be positive. But in letter B, what I'm going to do is I'm going to continue to use these things as my x2s. You could use them as your x1s, and then you could use 2 comma 4 as your x2. But I'm going to actually continue to use this, all right? Because it really gets at the idea of heading into 2 from the right and heading into 2 from the left. Although, actually, from your perspective, heading into 2 from the right, heading into 2 from the left. All right, again, let me do one manually. For instance, this is obviously going to correspond to the point 1, 1. So what I'll really be looking at is 1 minus 4 divided by 1 minus 2, right? So I think I can actually do that without a calculator. That's going to be negative 3 divided by negative 1, which is going to be 3. All right. Now what I'm going to do is I'm going to go back to my calculator technique. So let me make the TI-84 Plus big again. There's not a lot of room on this screen. I apologize. So there it goes, nice and big. And now I'm going to go back to that technique where I literally do, x2 squared minus x1 squared divided by y2 squared minus y1 squared. So let's do that for 1.5. Here we go. Parentheses, 1.5 squared minus 2 squared, parentheses, divided by, parentheses, 1.5 minus 2, parentheses. All right, make sure the calculation looks right. Again, I apologize. I know this seems probably contradictory to what I've been telling my students about in terms of always keep x2 larger than x1. I get that. Really, what I'm trying to do is, again, be kind of generic, allow that second x value to approach 2 from the right, approach 2 from the left, and I don't really want I don't really want to flip-flop my calculation right now because it really doesn't make a difference. Anyway, I hit enter, and hey, the pattern continues. I have 3.5. All right. Pause the video now and do all the rest of them in that table, and you'll see a pattern that is not all that surprising given what we found in letter A. All right, so for an x2 of 1.9, we got a slope of 3.9. 1.99, we got 3.999. Whoops, nope, sorry, one too many nines. For 1.999, there's our slope of 3.999, and then 3.9999. And again, what it appears as is that as x2 is getting very close to 2, but from the left, delta y divided by delta x is also getting very close to 4. And that's important, right? Because for a limit to exist, and now we're looking at the limit of a slope, right? For a limit to exist, it's got to be the same coming from both sides. All right? Now, at this point, we don't need our calculator anymore. So I'm going to put the TI-84 away, maybe until the back side of the sheet. All right, thank you. Pause the video now and write down anything you need to. All right, now I'm going to have to clear this out and go on to the next page, so I'm going to lose this thing. But again, the major conclusion that we came to is that we continue to see a tangent slope that seems to be approaching 4. All right? Now, I want to make sure that you really understand graphically what we're doing. So we're going to just draw some lines that we found in part A. Okay, don't worry about the ones from part B, although we could certainly draw them. There's no doubt about that. What I'm going to do, oops, I don't know why I just did that. So I've got my curve, right? And let's say that we had the point 2, 4, right, big point, right? What was that? The biggest thing we ever went up to was 3, so let me put the 3 on here. And then we had 2.5, and then we had 2.1. I know that's probably not actually 2.1. Now the idea here is that the first slope that we found, oh, this is going to be bad, but we'll give it a shot, was that, right? And it had a slope of 5. Then, when we drew the next one in, it kind of looked like this. There's almost no way for me to do this very accurately, especially with the thickness of this thing. And then we had a slope of 4.5. Right? And then we had one that looked like this. Now my picture looks really bad. And we had a slope of 4.1. And what's happening, let me draw a line in a different color. Let me go in green. Is that these lines are getting closer and closer to looking like our tangent line. Right? It's almost like we're taking that second point, right, this thing right here, and we're sliding it down the curve so that x2 is approaching x1. I can't let it get there. I can't let it get there, because if I let it get there, then the change in x would be 0, the change in y would be 0, and that would be problematic, right, when I divide the two. All right, but I can allow x2 to get as close to x1 as I want. Now, this is cool because we now have a way of getting the exact tangent slope. All right, now what I'd like you to do is draw one more picture for me. Okay, let's draw this parabola one more time, and we're going to set up a limit and show that the exact slope is 4. Okay, and here's how we're going to do it. And this was just brilliant, right? This is Newton's way of figuring this thing out. All right, I have the point 2, 4. And now what I'm going to do is I'm going to go over here to the point x and obviously x squared. All right, yes, is that obvious? Maybe I shouldn't say it's obvious, but it seems like it should be obvious. And what I'm going to do is I'm just going to set up an equation for the slope of that secant line, right? So the slope of that line, right, which is y2 minus y1 divided by x2 minus x1, right? So that's the slope of the secant, or the average rate of change over the interval 2 comma x, right? So it corresponds to 2, 4 and x squared. But what I want is I want to look at the limit of this as that point x heads to 2, right? And what we did is we did this exact process in the tables. In letter A, we looked at that limit as x went to 2 from the right. In letter B, we looked at that limit as x went to 2 from the left. Now, of course, upon substitution, what you get here, not surprisingly, is 0 divided by 0, right? Because that's all this, right? In that case, delta x is 0, delta y is 0. But that's where our slick limit techniques come in, right? At that point, I can say, well, I can factor x squared minus 4 as x minus 2 times x plus 2 divided by x minus 2. Those will cancel, substitute in, and there we go. Right? I have now proven that as I let the second point get infinitesimally close to the first point, the slope of the secant line, which then graphically becomes a tangent line, that slope heads towards 4. Isn't that neat? So that's then how I define the slope of the tangent line. I define the slope of the tangent line as the limit, let me write this right here, the limit of secant slopes as delta x goes to 0, right? And that's really the key. The change in x is going to 0. It forces the change in y to go to 0, assuming that the curve is continuous. And then we evaluate the limit using typically some kind of limit trick. Okay? So, pause the video. This is a very, very important development here. Write down anything you need to and think hard about what we just saw and did. All right, I'm going to clear this out. And we're going to do another one. Very similar. Very similar. All right, let's take a look at our half parabola, our square root function. We'd like to investigate and find the exact slope of the tangent curve at x equals 4. This time, though, instead of fixing the point 4, 2, we will choose points on either side of 4, 2 and allow them to get closer and closer until they almost meet. All right, so this is kind of cool. You know, in this case, what we're really doing, teeny tiny graph of the square root of x. Right, at this point what we're doing is, in order to figure out what the tangent slope is there, I'm going to take 2 points on either side. This is actually more similar to the approach that we did in the last lesson. And I'm going to find that slope of that secant line, and then I'm going to let those 2 points get closer and closer to my target point. Again, the thinking is still the same, which is that as I allow delta x to go to 0, right, then what's happening is I'm going to make that secant line closer to a tangent line. All right, let's see how to do this on the calculator. I'm going to bring it up right now. All right, so the TI-84 plus is back, okay? And now what we're going to do is we're going to find the secant slope, all right, for each one of those. Now, none of these numbers are nice. None of them are perfect squares, so this is going to get ugly, and we're going to do it on the calculator right away. But ultimately speaking, before I start chucking it into the calculator, a little writing down here, right? If I take this one down here, what I'm ultimately doing is I'm going to take the point at 3 square root of 3 and the point at 5 square root of 5, and I'm going to find the slope, right? And it's going to be root 5 minus root 3 divided by 5 minus 3, okay? So let's do that on the calculator right now. Okay, let me clear out the screen. I don't need that stuff there anymore. All right, now I have to be careful, depending on what OS you're using, you got to be really careful with the square root and the parentheses. This is the newest operating system on the calculator I've got on the computer, but some of the older ones on the TI-83 Plus, there's going to be more parentheses, so just be careful. If you get answers that aren't the same as mine, go back, look at your parentheses use, and really think about what's going on. All right, but let's do it. I'm going to put in a parentheses, square root of 5 minus square root of 3, I'll put in another parentheses, divided by, parentheses, 5 minus 3, parentheses. All right, let you catch up, take a look at what I've got, what you've got. Again, depending on your particular TI calculator, it may be different, and of course if you're using some other brand, Casio, Hewlett-Packard, all good, it might look very different. Anyway, let me hit enter. And we get a secant slope. It's a little messy. Got to get my notes here. 0.2520 ... Now I know I've always told my students around to 3 decimal places, but that's if we're doing an assessment or something like that. Right now I really want to kind of get a sense for what's going on here, so I want to write out quite a few decimal places. That's good enough for now. All right. Let's do one more of them together, then have you do the other 2 on your own. So let's do it. Let's put in parentheses, square root of 4.5 minus square root of 3.5, parentheses, divided by, parentheses, 4.5 minus 3.5. And another parentheses, step back, relax, take a look, see what it looks like. I think it's good. All right, hit enter. Okay, and we get m equals 0.25049, etc. Okay, well, take a little bit of time and do number 3 and number 4, and then we'll revisit. So pause the video now. All right, let's do it. So 3.9 to 4.1, if you've done it correctly, you'll get a slope of about 2.250019, etc. 3.99 and 4.01. Think about how small the delta x is at this point. The delta x is 0.02. Very, very small, right? Versus this, the delta x would have been 0.2 here. Whoops, not the m. Delta x. Here the delta x almost borders on being kind of large. It ends up being 1. Here the delta x is 2. Anyway, so here the slope is 0.25000019. So wow, look at that. And I bet letter B is a piece of cake. What value does it appear that these secant slopes are headed to as the width of the domain interval, the width, right, and that's just the measurement of delta x, of the domain interval, domain, approaches 0. And I bet most of you have a good sense that it's 0.25 or 1/4. All right? I would assume. But we don't have to assume anymore. We can actually prove it. All right, I'm going to get rid of actually quite a bit of this because I want to get myself some room. So use my eraser. Hey, bye. All right. Clean it all up. All right, now we're going to prove that this is true, but we're going to take the same approach that we took in the last problem. In other words, I'm not going to pick points on either side. What I'm going to do is take my square root function. I'm going to take the point 4, 2, and then I'm going to pick a point x, square root of x, right? I'm going to draw on a secant line. Oh, boy, I just totally didn't do that well. Sorry about that. That's not good. That's, I've been okay most of the day, and then that just happened. All right. let's try that one more time. Anyway, I'm going to go right from this point to this point, and we'll just kind of extend it backwards. I should have probably been doing that the entire time. Okay, let me mumble a little bit more. So we're going to be finding the average rate of change between 4, 2, and x comma root x, right? Now again, that's easy enough, right? The slope is going to be y2 minus y1 divided by x2 minus x1. Okay, and that's going to give me the average rate of change between any 2 points on this curve, assuming that they're different. But what I want to know is what happens to this slope as I allow that not fixed x point to get very close to 4. Now, I think that we can all concede that we'd get 0 divided by 0. And that's where our handy-dandy trick of rationalizing the numerator comes in, right? So I'll multiply numerator and denominator by root x plus 2, and I'll get the limit as x goes to 4 of x minus 4 divided by x minus 4. This is probably one of the easier rationalizing problems you've ever done. Those cancel, and now I can substitute in. I get the square root of 4 plus 2, and that would, of course, be 1 over 2 plus 2, which is 1/4. All right, so I did it. And again, the big picture here is that we're able to figure out the slope of the tangent line, which is also the slope of the curve. Remember, slope of the tangent line is how we define the slope of the curve. By setting up a secant line between two distinctly different x values, pinning one of them, and then letting the other one slide closer and closer. Again, the idea, very, very brilliant in its thinking by Newton, is that we fix this point here, then we allow this one to slide closer and closer to it, which turns that secant line into a tangent line. Isn't that kind of cool? All right, it's absolutely brilliant. And it's our first real true use of limits. Well, I guess we used them to find vertical and horizontal asymptotes and also continuity. But this is where they earn their money. All right, pause the video now. Think about what we did, copy down anything you need to, and then we'll wrap up the lesson. All right, gonna clear this out. Okay, get rid of the calculator, and let's wrap it up. I can't actually wrap. So today we saw a different look at tangent slopes, right, where we fixed a point and we allowed another point to get closer and closer to it. And then we were able to use that physical process of, hey, let me fix this one, take this one, let it get closer, 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 to then establish limits that will get us the exact value of the tangent slope. Now, the homework on this assignment, let me say, is a bit challenging. Try to stick with it. Try to work through it as well as you can, all right? Because it's going to lead us tomorrow to introducing possibly one of the most important concepts in all of mathematics, the derivative. All right, for now, let me thank you for joining me for another Arlington High School Math 4 Honors lesson. Until next time, I'm Kirk Weiler. Keep thinking, keep solving.